In 1962, Lars Hörmander, a 31 years old mathematician, won Fields Medal for his groundbreaking work in partial differential equations. Sounds boring? And you may also wonder why these equations are even relevant. Let me reveal exactly how these boring-sounding mathematical equations are basically acting behind the scenes and making your modern life different from the 1950s. We check the weather forecast on our phones and plan our next hiking or tour to a foreign land. Well, that's partial differential equations at work, making our life smooth. When you get an MRI or a CT scan, the machine doesn't actually take a photo from your inside. It just records hundreds and thousands of raw electromagnetic and X-rays from different angles. Then a computer solves inverse problem using partial differential equations and back calculates what the internal structure must look like based on how waves passed through it. A hot cup of coffee and a Wall Street stock option sounds totally irrelevant to each other, but in fact, they both follow the same mathematical laws. Basically, partial differential equations are the mathematical language of change and motion. They describe how heat spreads through metal, how waves move through water, how sound travels through air, and even how quantum particles behave. Lars Hörmander's genius was finding the master key that unlocks all of these systems at once, proving that whether it's fire, sound, or finance, the universe speaks one language, and that language is partial differential equations. Let's discover how this prodigy became one of the most influencing scholars who completely reshaped human life, and we don't even realize. Born in 1931, Hormander was a prodigy who rose through academia rapidly. Lars was truly exceptional. He was so advanced that he skipped 2 years of elementary school. During high school, he participated in a unique experimental scheme where students only had to spend 3 hours a day in class, leaving the rest of the time for independent study. He flourished in this environment, often teaching himself advanced topics far ahead of the curriculum. He earned his master's degree from Lund University at just 20. By 1955, at just 25 years old, he had completed his PhD. And at age of 25, he already laid foundations of his groundbreaking and was appointed a professor at the University of Stockholm. Imagine you drop a pebble into a perfectly still pond. The ripples spread outward in circles. A partial differential equation is what mathematicians use to predict exactly where those ripples will be at any moment in time, how tall they'll be, and how fast they're moving. Now imagine dropping 100 pebbles at random places with rocks of different sizes, all at different times, and asking, what will the water surface look like in 10 seconds? That's the kind of complexity PDEs handle. These equations are everywhere in physics, engineering, and the natural sciences. But here's the problem. Solving them is incredibly difficult. In fact, for many PDEs, we still don't know if solutions even exist, or if they do, whether they're unique or smooth. He discovered the property we know as hypoellipticity. This property gave mathematicians a precise test, a way to look at a differential equation and determine whether it has this smoothing property. It's like he handed everyone a universal detector that could instantly tell them whether their equation would produce smooth solutions. This work, along with his geometric explanation of why certain equations can't be solved at all, the Louis phenomenon, and his use of Fourier analysis to understand distributions, earned him the Fields Medal in 1962. He is one of the very few mathematicians to receive the triple crown of the field, the Fields Medal, 1962, for his early breakthroughs in solvability, the Wolf Prize in 1988 for his lifetime of leadership, and the Steele Prize in 2006 for his unmatched ability to explain complex ideas. Beyond the trophies, his true legacy lies in his 4-volume masterpiece, The Analysis of Linear Partial Differential Operators. Known simply as the Bible of the field, these books transformed a chaotic collection of mathematical tricks into a unified, rigorous science. But perhaps his greatest legacy isn't the medals or titles, it's the impact of his work. Hormander's theories continue to influence modern mathematics in areas you might not expect: probability theory, differential geometry, and even the study of Boltzmann's equation in statistical mechanics. Every mathematician working in PDEs today stands on the foundation Hormander built. His books are still the first place graduate students turn to when they need to understand linear differential operators. His techniques are still being applied to new problems. Thanks for watching. If you enjoyed learning about Lars Hörmander, please like, subscribe, and let us know in the comments.
This is Awards, where the world's greatest minds live forever. Don't just watch history, be inspired by it.